All right, thanks for watching. And today I would like to talk about convergence in Rn and more generally in metric spaces. So let me just remind you what it means for a sequence of real numbers to converge to S. Well, Sn converges to S if for all epsilon there is a capital N such that after this threshold, capital N, we have that Sn minus S is less than epsilon. So again, the idea is as follows. If you have a sequence that converges to S, kind of like that, what does that mean? It means that no matter how small the error is, there is a threshold such that after this threshold, you're in the good region, if you want, of radius or size epsilon or 2 epsilon. So this is the good region. And again, what it means is eventually you're always in the good region. And the good news is this definition is almost the same in metric spaces. The only difference is you replace the absolute value with your distance. So, more generally, definition, if SD is a metric space, and Sn is a sequence in S, then Sn converges to S if, namely, for all epsilon, there is a threshold, capital N, such that after this threshold, so if n is bigger than capital N, then not absolute value of Sn minus S, but this time just the distance between Sn and S is less than epsilon. So literally the only difference. Okay. Now, even though the definitions are similar, the visualization is slightly different. So in this case, what we would like to say, before the region was a strip of radius epsilon, but this time the good region is actually a ball of radius epsilon. Because again, we want to look at all the points whose distance to S is less than epsilon. So again, we have the good region here. And same idea, if Sn converges to S, it just means eventually your sequence Sn is in the good region. So no matter how small epsilon is, eventually, so after this threshold, capital N, we have that all the values of your sequence are in the good region. All right, and now let's talk about convergence in Rn, or here we call it Rk. And the good news is, because Rk is a metric space, we can just apply everything that we talked about before to Rk. And the nice thing is, the definition of convergence is exactly the same as the definition I wrote down before. And that's again the beauty of math theory. We just generalize everything. But let me just remind you some facts about Rk. So Rk is just a set of points, capital X, which are of the form x1 up to xk. And where again each component is a real number. And moreover, you have the distance between x1 and xk and y1 and yk. It's again just the R2D2 distance, so just the square root of sum of squares. So y1 minus x1 squared plus dot 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 plus yk minus xk squared. All right, and now another thing, well, here's the thing. From problem is we use x1 up to xk for indices, like for components. So we can't use that for sequences anymore. And really, to make things a bit clearer, we'll put the indices for sequences on top. So really, sequences will be written as follows. It's slightly confusing, but it's just written as xn, which if you want, it's xn1. So it'll be written as xn, but the thing is, each value of the sequence is just a point in Rk. So really the components are x1n up to xkn. So again, for every number n, let's say 2, I give you a point x12, x22 up to xk2. So it's really the top here that matters. Don't worry too much about the bottom thing. All right, and then what does it mean for a sequence to converge? So definition would simply say xn converges to x if, for all epsilon, there is capital N such that if capital N, so if n is bigger than that threshold, then the distance between xn and x is less than epsilon. No parentheses here. So in other words, it's exactly the same definition as before, except before we use a general distance, but now we use that square root kind of distance. But here's the nice thing. We never need that definition again. And here's why. Consider the following sequence. Let's say in R2. Again, xn to be just the sequence 1 over n and e to the minus n. And again, this is the component x1n, and this is the component x2n. Now, question, what does this converge to? Well, if you let n go to infinity, and this is very important, this goes to 0, and this goes to 0. So what have you done? To figure out where this converges to, you looked at the limit of the first component, and you looked at the limit of the second component. And in fact, this will always be true. Namely, a sequence in Rk converges if and only if each component converges. And so this is the main théorème du jour, so theorem of the day, namely xn converges to x if and only if every component converges. So for all j, xnj converges to xj. And again, what is xj? It's just all the components of x. So it's the jth component of x. All right, and again, a sequence in Rk converges if and only if each component converges. And in fact, in some sense, it makes sense, because what does that mean for a sequence of points in Rk to converge to x? Well, in some sense, it means this diagonal gets as small as possible, because xn converges to x. But then what is the components? It's just the two legs of the triangle. So the first component is this minus this, and the second component is this minus this. And then what we're just saying is, if this diagonal gets very small, then each leg gets very small. And moreover, if each leg of the triangle gets very small, then the diagonal also gets very small. In order to prove that, let's just prove one more lemma, which will be very useful. I promise you, once we prove that lemma, then the rest of the proof flows like butter. So consider the following thing. So d of the distance between 2 points, x1 and xk, and y1 and yk. Now, this has nothing to do with sequences. Just consider points, x1 and x1 up to xk, and y1 up to yk. And think of this, if you want, as the hypotenuse of a triangle. This is the distance, and on the one hand, it turns out, of course, the hypotenuse is bigger than the length of any of its legs. So in other words, if you consider, let's say, any other leg, let's say the distance being xj minus yj, then this distance is always bigger than the length of its leg. So in other words, for all j, again that's for 1 to k, we have that on the one hand this distance is bigger than xj minus yj. On the other hand, and that's slightly weirder, so we want the hypotenuse to be smaller than some length. Okay. Now, the problem is the hypotenuse is bigger than each leg, so it cannot be smaller than each leg. But consider the following one. Take the biggest value, the biggest leg. Let's say here the second one is bigger than the first one. So take kind of the maximum and take square root of 2 times the maximum. Because here we have 2 legs, so square root of 2. And in general, square root of k times the maximum. Then it turns out this huge leg will always be bigger than the hypotenuse. In other words, the hypotenuse will always be less than or equal to a constant times the biggest leg. And this is what the second thing is saying. That's less than or equal to square root of k times the maximum of, let's say, x1 minus y1 up to xk minus yk. So it's really a squeeze theorem for distances in some sense. All right, and let's prove this, and the good thing is this gibberish I talked about is as long as the proof itself, so the proof is not bad at all. So, proof. Pretty straightforward, I would say. So take the distance between x1 and up to xk and y1 up to yk. Well, by definition, that is just the square root of the sum of squares. So y1 minus x1 squared plus dot 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 plus, let's say middle term is yj minus xj squared plus dot 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 plus yk minus xk squared. But here's the thing, so we want to prove greater or equal, each term is positive, etc., etc. So in particular, this huge square root is bigger than or equal to the square root of the middle term. So it's bigger than or equal to square root of yj minus xj squared, and that's just absolute value of yj minus xj. And that is true for every j. So on the one hand, this has been proven, and now let's show this thing. So let's call capital M to be that max. Let capital M be the max of x1 minus y1 dot 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 xk minus yk dot dot dot. Okay? And we just want to show that the distance is less than square root of k times m. But then also this is not too bad. Take the distance between x1 up to xk and y1 up to yk. So that becomes the square root of y1 minus x1 squared plus dot 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 plus yk minus xk squared. But here's the thing. You see, because m is the maximum, each of the components is less than or equal to m. So the square is less than or equal to m squared. So really, this becomes, this whole square root is less than or equal to square root of m squared plus m squared plus dot 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 plus m squared. But how many terms are there? There are k terms because we're in Rk. And that becomes square root of k times m squared. But that's square root of k times m. And that's what we wanted to show. The distance is less or equal to square root of k times this maximum leg. Okay, and that was the hard part. Now let's just prove our theorem. So I think that's the easier part. Again, remember what is the theorem? It says that the sequence converges, so xn converges to x, if and only if each component converges, so for all j. Okay, no problem. It's just an application of this inequality. So here's the thing. So first of all, let's prove this part. So let epsilon be given. Then, since the sequence converges to x, there is capital N such that if n is after that threshold, then d of xn comma x, so the distance between x and x is less than epsilon, but that's just the same as saying d of the first component up to the kth component and the component of the limit is less than epsilon. But now remember, we had this beautiful thing that the distance of the hypotenuse is bigger than any of its legs. So this is actually bigger than the absolute value of xj and minus xj. So the jth component of this minus the jth component of this. But then what do we get? So with that same capital N, so with that same capital N, if n is bigger than capital N, then in fact with this chain of inequalities we get xjn minus xj is less than epsilon. So here j was arbitrary, so for all j, x and j converges to xj. You see? So again, what do we have? Essentially the hypotenuse becomes small, so each leg is small, which forces the component to converge. On the other hand, again, very similar, so let epsilon be given. Then if you want, what do we know? We know xn1 converges to x1, so there is n1 such that if n is bigger than n1, then the component xn1 minus x1 is less than, usually, epsilon works, but to make it elegant, let's put epsilon over square root of k. And then similarly, now we know the second component converges, so x2n converges to x2, so there is n2, such that if n is bigger than n2, then xn2 minus x2 is less than epsilon over square root of k, and so on and so forth until you take the kth component. So xnk converges to xk, so there is nk such that if n is bigger than nk, then xnk minus xk is less than epsilon over square root of k. So what are we saying? We're saying that every leg is less than epsilon over square root of k. So in particular, the biggest possible leg is less than epsilon over square root of k. And that allows us to conclude. So now, so if n, so we want all of those things to happen, so let capital N be the bigger one of all of those. So the maximum of n1 up to nk. Then if n is bigger than capital N, what do we get? So again, let's look at the distance between our sequence and our limit. So dx n and x, which again is the distance of the point xn1 dot 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 xn xnk and x1 up to xk. Again, which now we know by our distance squeeze theorem in some sense, it's less or equal to square root of k times the maximum of the first component and the second component and the kth component minus xk. But the whole point is each of those components is less than epsilon over square root of k. Less than epsilon over square root of k. Less than epsilon over square root of k. And so the whole thing, so the maximum is also less than epsilon over square root of k. So this whole thing becomes less than square root of k times epsilon over square root of k. And we get epsilon. So again, for any epsilon, there is a threshold big enough such that after this threshold, this distance is less than epsilon. And therefore, what can we conclude? We conclude that xn converges to x.